Our topic today is Newton's laws of motion and its applications. In this study, we will be considering the statements on the laws of motion, meaning of inertia, momentum, and impulse. We'll be considering the applications of Newton's laws of motion in terms of collision of bodies, recoiling of gun, propulsion of the rocket, and that of the jet. This is an extension of the work on motion. Newton's laws of motion and its application. Newton's laws of motion are in three forms. The first law states that a body continues in its state of rest or uniform motion unless a force acts on it. It is also called the law of inertia. The second law states that the rate of change of momentum is proportional to the applied force, and it takes place in the direction of the force. The third law states that action and reaction are equal and opposite. From Newton's second law of motion, we get that force is equal to mass times acceleration, or force equals mass times the difference of the final velocity and the initial velocity divided by the time taken. The change in the momentum of a body is equal to the impulse. Change in the momentum is equal to impulse. The change in momentum is mass times the difference of the final and initial velocity. And impulse is the product of force and time. Impulse is defined as the product of the force acting on the body and the time it acts. Next is the law of conservation of linear momentum. The law states that the total momentum of a system is conserved provided no external force acts on that system. The law of conservation of linear momentum is a combination of Newton's second and third laws. In collision terms, the law of conservation of linear momentum is simply the total momentum before collision is equal to the total momentum after collision. Also, for a triggered gun, the change in momentum of bullet is equal to the change in the momentum of the gun. Example 1. In an experiment, a constant force is applied to several masses M, and the corresponding accelerations A are measured. Which of the following graphs correctly represents the experiment? Graph 1 is graph of acceleration against mass of different patterns. The options are A, 1 and 2, B, 2 and 3, C, 3 and 4, D, 2 and 4. Selection process. From Newton's second law of motion, force is the product of mass and acceleration. Therefore, acceleration is equal to force over force divided by the mass of the body. From this equation, acceleration is inversely proportional to the mass, and therefore equations 2 and 4 are correct. Option D is correct. Example 2. A body of mass 0.15 kilogram is kicked against a rigid vertical wall with a horizontal velocity of 50 meters per second. If it rebounded with a horizontal velocity of 30 meters per second, calculate the impulse of the ball on the wall. The options are A, 4 Newton second. Option B, 7.5 Newton seconds. Option C, 12 Newton seconds. And option D, 15 Newton second. Solution. Impulse is equal to change in the momentum of the body. Where there is rebound, impulse is equal to mass times the sum of the initial and the final velocity. Impulse I will now give me the mass is 0.15, final velocity 30, initial velocity 50. Impulse will give 0.15 times 80. Impulse is equal to 12 Newton second. The answer is option C. Example 3. An object of mass 2 kg moves with a velocity of 10 meters per second round a circle of radius 4 meters. Calculate the centripetal force on the object. The options are A, 100 newtons, B, 50 newtons, C, 40 newton, and D, 25 newton. Solution. The centripetal force F is equal to mass times acceleration. where A is the centripetal acceleration. But A, the acceleration, is velocity squared over the radius for circular motion. Therefore, the centripetal force is mass times V squared over R. Centripetal force F is mass, which is 2V 100 squared divided by, 10 squared. The velocity is 10. 10 squared divided by 4. F will give 2 times 25, which is 50 Newton. Option B is correct. Example 4. A moving car of mass 800 kg experiences a frictional force of 200 Newton. If it accelerates at 2 meters per second square, calculate the magnitude of the force applied to the car. Option A, 2,400 newtons. Option B, 2,000 newtons. Option C, 1,800 newtons. And option D, 1,600 newtons. The solution to the problem is as follows. Let F represent the applied force to the car. Small f represents the frictional force. And F subscript R represents the resultant force on the car. The resultant force is the difference between the applied force and the frictional force. MA is equal to applied force minus F. M is 800, acceleration is 2, applied force is unknown minus frictional force, 200 Newton. 1,600 is F minus 200. The applied force is 1,600 plus 200. The applied force is 1,800 Newton. Option C is correct.